first devices. They focused on battery efficiency, touch interfaces, and app-centric ecosystems. Features like sandboxing and permission models became standard to protect user data. This shift forced operating system designers to think differently about interaction, energy use, and security. Finally, in the modern era, operating system design has expanded beyond local devices into the cloud. Chrome OS in 2011 pioneered the browser-centric OS model. Windows and Mac OS now tightly integrate with cloud services like OneDrive and iCloud. We are also seeing operating system trends towards AI integration, IoT devices with microkernels, and even quantum-ready operating systems in research. The OS is no longer confined to your laptop. It extends to your phone, your smart devices, and even distributed systems in the cloud. So, from switches to AI, the journey continues. Now, operating system types. We discussed what are the different types of operating system. Yeah. First is the Okay. Now we have seen the history and evolution. Let us classify operating system into major types based on how they handle workloads and users. We will look at batch operating systems, multi-programming operating systems, real-time operating systems, and mobile operating systems. Each was designed to solve specific computing problems. Even though modern operating systems often combine features, understanding these categories help us appreciate their design trade-offs. Batch operating systems. Batch operating systems were the earliest types of operating system. Jobs were collected into batches with similar requirements, then operating system executed them sequentially, one after the other, with no user interaction in between. Once a job is started, you have to wait until it was done before the next job could run. The advantages were very efficient for repetitive large-scale data processing things like payroll, billing, and scientific calculations. The limitations were there was no interaction with the user and debugging was very slow and turnaround time was very long. You may have to wait for hours even for a single typo mistake. So because debugging was very slow here. Even today, batch concepts survive in things like enterprise job schedulers and scientific clusters. Then, multi-programming operating system. Multi-programming operating systems has improved efficiency dramatically. The idea was to load multiple programs into the memory at once. If one program is waiting for input-output, another can use the CPU. This ensures the CPU is almost never idle. The operating system switches between programs using context switching. This was the foundation of multitasking and is still at the heart of Windows, Linux, and Mac operating system today. Environments where multi-programming thrives are mainframes, shared servers, and multi-user systems, where maximizing hardware utilization is critical. Real-time operating system. To which we call as RTOS. So these were designed for environments where timing was everything. There are two types of real-time operating system, hard RTOS and soft RTOS. Hard RTOS where deadlines must never be missed. You cannot miss the deadline. If operation has to be executed within a time frame, it has to be. For example, aircraft control, medical equipment, automotive safety systems, These all are the examples of hard real-time operating systems. On the other hand, soft RTOS, where occasionally you can miss the deadlines and these are tolerable. For example, video streaming, gaming, multimedia apps. All these are soft real-time operating systems. RTOS prioritize deterministic timings over throughput. Predictably matters more than your raw speed. RTOS structure and architecture and requirements. An RTOS is structured differently from a general purpose operating system. Its core requirements include deterministic timing and predictable latency, priority-based scheduling, minimal interrupt latency, reliable inter-process communication, memory protection to prevent interference, and its architectural components include a scheduler, which decides what runs and when, task manager, which creates and monitors the task, interrupt handler, which is used to respond to an event, memory manager, which allocates memory safely, timer services, and device drivers. Notice that how everything is streamlined to guarantee responsiveness. RTOS kernels are much smaller than general and operating system kernels. Then mobile operating systems. Okay, so finally, let's look at the mobile operating system which emerged in the 2000s and changed the computing landscape. Examples includes your Android, which is Linux based, highly customizable and dominate the market share. Another one is iOS, which is based on the Darwin's kernel, tightly controlled and optimized for Apple hardware. One more is there Harmony OS, which is it is a newer microkernel approach focusing on cross-device integration. There are some key design considerations. First one is the resource optimization. The resource optimization is balancing the performance with battery life. Then interface design, which is touch, gestures, and accessibility. Then connectivity, seamless Wi-Fi, cellular and cloud integration. Security, sandboxing, permissions, and encryption. The mobile operating system continues to evolve with AI assistants, augmented reality, and cross-device experiences. Understanding the operating system structure and components. Now that we have looked at the operating systems types, let us zoom into the structure of an operating system. Most operating systems are built in layers, and each layer provides services to the layer above it. The lower layer handles the hardware, and the higher layer focuses on the user interaction. At the very center is the kernel, which is the heart of the operating system. This is the privileged software that manages CPU, memory, devices, and the security. Everything else depends on the kernel's ability to orchestrate resources efficiently. The kernel. So let us discuss about the kernel. There are basically monolithic kernel, microkernel, and hybrid kernel. Monolithic kernel, all services run in the kernel space as one big process. It is very fast, but a single bug can crash the whole system. For example, Linux and Unix. Microkernel, in which minimal core runs in the privileged mode. Most services run as the user processes. More stable and secure, but performance is lower. For example, Minix and QNX. Hybrid kernel a practical mix of some services in the kernel mix, some in the user mix. So it balances performance and stability. For example, Windows NT and Mac OS. So when operating system designers chooses a kernel, they are really making trade-offs between the performance, reliability, and complexity. So these are the basically kernel architecture comparison. Now, key operating system components. Beyond kernel architecture, operating system have some core components that work together. One is the process management. The job of process management is to create processes, schedule processes, and synchronize processes. Another component is memory management, which allocates memory, protecting address spaces, paging, and segmentation. File system management, organizing files and directories, permissions and recovery. Then device management, which includes drivers, input-output scheduling, and interrupt handling. And one more component is there, which is the security and access control. It includes authentication, access lists, encryption, and sandboxing. So each of these is a subsystem, but together they create the seamless environment that lets users and applications interact with hardware safely and efficiently. Then user interfaces. User interfaces are the bridge between the human and operating system. The first user interface is the CLI, which is the command line interface. It is precise, scriptable, great for automation, but steeps learning curve. Examples are Bash and PowerShell, where you write the commands and execute, where you need to give each command. Another one is GUI, which is the graphical user interface, which is very intuitive, visual, user-friendly. Examples include your Windows Explorer, Mac OS Finder, but it is easy to use, but it is heavier on the resources. Emerging interfaces includes nowadays touch screens, voice assistants like Siri and Google Assistant, AR, VR, even experimental brain-computer interfaces, where you can think of a command and it executes. No matter how advanced the interface, they are all built on the same operating system fundamentals we have been discussing. The invisible conductor. I like to describe the operating system as an invisible conductor of a digital orchestra. It coordinates all the instruments, CPUs, memory, input-output devices so they can play in harmony. It makes sure no single instrument drowns out the others. And it creates a cohesive performance that the user experiences as a smooth and seamless computing. When the operating system is designed well, you do not notice it, but it just works. That invisibility is actually a sign of its sophistication. Have you ever noticed that operating system only when it failed, like during a crash or freeze? That shows how invisible it usually is. So thank you. That brings us to the end of week 1, which was the introduction to operating system. We have covered the purpose and rules of operating system, their history and evolution, types of operating systems, which includes batch, multi-programming, and real-time and mobile operating systems, kernel structures and components, which included monolithic and microkernel. And then we discussed about the user interfaces and the CLI, GUI, and the emerging technologies. In the next unit, we will start digging deeper into the process management, how the operating system creates, schedules, and manages the processes. This is where we will begin to see the real mechanics of operating systems in action. Thank you.